Throughout this video, keep in mind, a mutation is a change in a DNA sequence of an organism, such as your detective here. He normally should have 2 brown eyes, but because of the point substitution missense, the mutation, it affected him, so he has 1 brown eye and 1 blue eye. Every case starts with a mystery. This one, my own eyes. 1 brown, 1 blue, but why? What's the cause? What's the culprit? Tonight, I will crack the case. Baby girl, let me see you do your dance, let me see you twirl. My name's Blue. I'm investigating a case. You've got heterochromia like me. What's your story?
Ah, a fellow mystery seeker. I'm Mickey, you see. Melanin controls eye color. My blue eye has less melanin. My brown eye has more melanin.
So melanin is the key? When it's missing, the eye's blue?
That's right, and melanin productions is controlled by genes.
Genes, huh? Got a name?
OCA2, it's the one you want to look at. Mess with it, and melanin productions go wacky.
Interesting. That's clue number 1. Time to follow the trail. Thank you, Mickey. Detective Blue pinned clue number 1. Melanin controls eye color to his crime board when he gets back to his office. You are a hard one to find.
I'm Lou. The woods are my ally detective. You seek knowledge?
I do. I've heard you got experience with melanin.
Melanin. It shapes not only the eye color, but feathers, fur, and skin. But the real mystery is the genes that control it.
OCA2, right? I've heard it plays a role.
Indeed, but it's more than just a name. This gene encodes the P protein, which regulates melanosomes, which are compartments where melanin is made. If something alters OCA2, melanosomes don't function properly.
So a faulty OCA2 means uneven melanin production?
Exactly. And that, my friend, is why our eyes tell 2 different stories.
Clue number 2 down.
I heard you need answers. Lucky for you, I run the best forensics lab in town.
Dr. Ivory, I need you to analyze my OCA2 and my DNA. Dr. Ivory takes the sample and runs it through a machine.
This, my friend, is where we find the mutation. Detective, we need to talk about the transcription. It's the key in your case to understanding the OCA2 gene is supposed to work before it was messed up by the mutation.
Alright, Doc, I'm all ears, but keep it simple. I work with fur and footprints, not fancy lab talk.
Okay, so think of DNA like your big locked up case file, the master of everything.
So like my evidence cabinet?
Yes, exactly. It has every detail ever needed, but you can't just slap it all on your crime board. You need to pull out specific evidence you need, like the OCA2 gene.
Okay, keep going.
Now that we've got our case file open, we need to copy down the important details. This is a transcription, but we don't copy it word for word. Instead of writing it in the same language, we translate it into something that lab can read, which is the messenger RNA or the mRNA.
So like making a case summary instead of lugging a whole cabinet around?
Exactly, but here's the catch. DNA and RNA have special code. The letters are A, T, C, and G in DNA. But when we make mRNA, we swap the T for U. So adenine A pairs with uracil U. Cytosine C pairs with guanine G. And thymine T gets replaced by adenine.
Got it. So the OCA2 file gets copied into a new format. But what happens after that?
So that's what the transcription does. And think of the RNA polymerase like you. You step in, type up, and copy specific evidence because you can't take everything out of your evidence cabinet.
So I like RNA polymerase, huh? Making an extra copy just like mRNA transcription?
Bingo! But just remember, the copy isn't exact. It's working version. Instead of thymine T, it's used uracil U. Just like how your typed version might be a summary instead of a handwriting duplicate.
Okay, so I have the mRNA evidence transcript thing. Now what?
So now the transcript can leave the nucleus or your evidence cabinet and go straight to the protein factory.
Wait, why not just take the original case file?
Great question, Detective. The original DNA is way too important to risk damage. It stays locked up for safekeeping. Instead, we make an RNA copy so the instructions can get where they need to go without putting the whole case at risk.
I'll pin this to my board in just a second. But just like this copy helps me crack the case, the mRNA tells the cell how to make the correct protein. But in my case, the mutation scrambled the instructions, so it doesn't know what protein to create.
Yes, you got that right. That is why your eye is blue instead of brown. A small typo in your DNA which makes your mRNA incorrect in your transcription, so the P protein can't be made properly.
Phew, I think I'm understanding. The mutation messed up my evidence file, and that's why my eye has a different story to tell. Alright, Doc, one more clue on the board. We're closing in on the culprit. Thank you for all your help, but I'm still a tad bit confused. I understand the transcription. The mRNA is my typed cell case file, a copy of my OCA2 evidence. But how does that turn into protein, and where does it all go wrong?
Ah, that is where the translation comes in. Okay, so think of this. You have your mRNA right, but typing a report does not solve the case. All by itself, you need someone to read it and take action.
So, who's reading my report?
The ribosome is like your police station's action unit. They will take your typed report and translate it into real-world action, just how a ribosome reads mRNA and then assembles the protein.
So the ribosome reads the mRNA in 3 sets of letter codons. Each codon is like an order given to the squad. One codon says bring amino acid A, the next says add amino acid C, and so on. The amino acids are building blocks for the protein. Alright, Detective, let's put it together. This whole operation starts in the nucleus when the cell needs a protein. It opens up the DNA case file and makes an mRNA copy of the OCA2 gene. That's transcription. Once the transcription is ready, it leaves the nucleus and heads to the protein factory, the ribosome. At the ribosome, another team comes to transfer RNA and tRNA, bringing it to the right amino acids like puzzle pieces to build the protein. This is translation. By the time they're done, the cell has the final product, a working protein that affects fur, feathers, or even eye color like you. So if everything is working right, the P protein gets built and melanin production runs smoothly?
Yes, but your report has a slight issue. Your OCA gene has a point mutation, meaning one codon is wrong, so your ribosomes read faulty instructions instead of making perfectly functioning P protein and producing a broken version that doesn't do its job.
Oh my god, that means my melanosomes in one eye don't get enough melanin they need because of one small mistake in translation, and then one eye doesn't get enough melanin, so it's blue instead of brown. Okay, I need to pin this all to my board. I'll see you tonight.
Well, Doc, that's another case cracked. OCA2 was the culprit. Feels good to have the answers. My own mystery solved.
Indeed, Detective. Genetics can be a tricky thing, but with the right clues and sharp mind, the truth always comes to light.
Never thought I'd be my own biggest case, but I gotta admit, it was a good one. Science, mystery, and a little bit of luck.
Luck? No. Science is all about precision. Mutations seem like random chance, but every twist in DNA tells a story. And your eyes, well, they tell a story of their own.
A story of typos and transcripts, coughs and codons.
And a small genetic hiccup make you a unique husky you.
The end.